One of the key and most important decisions when using Aspen Plus is the selection of the property method. A property method is a set of models used to calculate thermodynamic, kinetic, and transport properties. If the components that you select do not work with Aspen Plus default or recommended methods, then you have the possibility to modify these methods. Now, to put it simply, the thermodynamic method, which is a subset of the property method, can be classified as an activity coefficient-based method or an equation of state method. Let's start with the activity coefficient-based method. This method is mainly described for subcritical and non-ideal liquid systems at pressure below 10 atmosphere. In this method, the incorporated parameters within the model are temperature dependent. Therefore, such a method becomes problematic in the critical region. Now, before going into detailed discussion on solution thermodynamics, let me first simplify for you the concept of ideal versus non-ideal liquid mixture. In general, in chemistry, mixing two or more similar species to form a solution results in an ideal liquid mixture. Take a look at this example here. For example, mixing benzene, that you can see here, with toluene forms an ideal benzene-toluene mixture, and so is the case with methanol-ethanol mixture. The similarity among chemical species is exemplified in terms of equal number and the same type of functional groups to a large extent, and of the length of the hydrocarbon chain of the molecule to a small extent. The deviation from an ideal liquid mixture, or in other words, the formation of non-ideal liquid mixture, arises from mixing chemical species characterized by different chemical activities and different functional groups. For example, mixing ethanol, that you can see here, with benzene forms a non-ideal liquid mixture, as benzene and ethanol are of two different categories. Also, mixing of ethanol with hexanol, that you can see here, also shows some sort of deviations from ideality compared with mixing of ethanol with methanol, because ethanol and methanol are quite similar in terms of chain lengths. From solution thermodynamics point of view, the non-ideal liquid mixture can be described by introducing the concept of fugacity, which basically accounts for the effective thermodynamic presence of a specific species in a solution. This means that its thermodynamic concentration not only reflects its count, but also extends to include its social interaction with its neighbors, the so-called activity coefficient. So, this was a brief description of the activity coefficient-based method. Let's now shift our attention to the equation of state method. The equation of state model operates in the critical region and when there are no polar components. It describes the relationship among the three variables: pressure, temperature, and volume. It has few binary parameters that extrapolate well with temperature. We can use equations of state model over wide ranges of temperature and pressure, including a subcritical and supercritical regions. For ideal or slightly non-ideal systems, thermodynamic properties for both the vapor and liquid phases can be computed with a minimum amount of component data. An equation of state model is suitable for modeling hydrocarbon systems with light gases. For the best representation of non-ideal systems, we must first obtain binary interaction parameters from regression of experimental vapor-liquid equilibrium data. We'll see this in detail further ahead. For now, the most common examples of equation of state models are listed here. Now, since the selection of a property method for a given chemical component has the first priority, Aspen Plus provides what is called the Property Method Selection Assistant or Wizard. That function can be reached via clicking on the Method Assistant button that you can see here under Tools. So let's click on it. Once you click on Methods Assistant, Aspen Plus Help window pops up, as you can see here. And here you have to opt between two choices. Select Component Type or Process Type. But don't panic, because both choices will guide you. In our example here, let's select Specify Component Type. As you can see here, the Help window updates the content and shows you 4 different component-based categories out of which you may select. For example, if you select the first category, which is Chemical System, and further select the pressure to be less than or equal to 10 bars, then the recommended property method will be Activity Coefficient Based Method as seen here. So you can use NRTL, Wilson, UNIQUAC or UNIFAC. Let's go back to the previous window. Now, the second category that you can see here better describes hydrocarbon systems, so non-polar systems. The third category is dedicated for some special applications, such as amine systems, electrolyte systems, or sour water systems. And the last category is reserved for refrigerants. Okay, now let's go back to the initial window of the Assistant Wizard and select this time Specify Process Type. Here you can see the new result of our choice. Notice that for chemical, environmental, gas processing, petrochemical, power, and refining processes, these are additional subcategories from which you can pick up your choice. This, in turn, will further refine the number of property methods recommended by Aspen Plus Property Method Wizard. For example, if we select the type of process to be chemical, as seen here, then the next window shows what property methods are recommended by Aspen Plus. As you can see here, Aspen Plus Property Method Wizard recommends the Activity Coefficient Based Method for a general chemical process with a pressure less than or equal to 10 bar, and recommends the Equation of State method with advanced mixing rules for a pressure greater than 10 bars. Now, as said earlier, some specialty chemical processes are also pinpointed as subcategories of chemical processes, such as azeotropic separations and carboxylic acids, listed here below the recommended property methods. Remember that the deeper you dive below the surface as you move from the main into a subcategory of a chemical component, the higher the accuracy and predictability of the Aspen Plus recommended property method will be. There are special common applications where Aspen Plus gives them extra attention in terms of model accuracy and predictability. Okay, one last thing before we finish off this video. Take a look at the following figure. It shows you the tree for the property method selection, which is based on different categories, such as the nature of medium, so is it polar, is it non-polar, is it electrolyte or non-electrolyte, is it an ideal mixture or a real mixture, and the operating conditions, high versus low pressure. For example, if your chemical process uses butane at 35 atmosphere, then based on this figure, if you select non-polar, which is the case of butane, then real, the most relevant property methods for your case would be the Pang-Robinson model. Now, this figure is available in the downloadable resource section. Now, before moving on to the next video, keep in mind that the property method selection will be revisited in each successive section, as it is the heart of any simulation process. Hopefully, toward the end of this course, you will master the process of property method selection based on the given chemical process being handled. What I want you to keep in mind at this level is that the idea behind presenting the choice of having more than one property method for a given process system is simply that one method may be superior to others in terms of getting a converging solution and realistic results. As you will see further ahead in this course, a given property method may fail to end up with realistic or reasonable results. In fact, it may not even converge to give a solution. For this reason, the built-in property method selection assistant will narrow the search circle for you in order to try alternative property methods when the first suggested or default method failed to give reasonable results. Of course, it is intuitively assumed here that you have properly entered the flow rates, their components, their operating conditions, and any other physical, chemical, or thermodynamic constraint imposed for the process you want to model. Finally, as we shall see in a later section, you may assign a property method for a specified section, which is different from that assigned for the rest of the process flowsheet. By default, Aspen Plus assigns a section called Global for the entire process flowsheet. However, you may define a new section where it may comprise existing or newly added blocks. This will be covered in detail in later sections. In the next video, we will demonstrate a practical example of how we can further improve the accuracy of a property method.